What's going on? Alright, so I'm going to go through this problem here. Find critical and pseudo-critical edges in a minimum spanning tree. Rated hard, 66 ups. Alright, so the good thing about doing this problem is just the fact that if you do this problem, you have to learn union find, and you have to learn Kruskal's algorithm to find minimum spanning trees. Then you have to add on a little bit of trick, to be able to really see what is critical and what's pseudo-critical. So that's the basic thing. So that's what the code looks like. But before we look at this, here we go. Given a weighted undirected connected graph with n vertices numbered from 0 to n-1 and an array edges where edges I is this. So yeah, so you have a from and a to, and you have a weight. It represents a bidirectional. Oh, this is bidirectional. Right, so that means this is an undirected graph. I mean, bidirectional means it goes in both directions. So from to, but it goes to go. Okay, but anyways. And weight edge between nodes from and to. A minimum spanning tree, MST, is a subset of the edges of the graph that connects all vertices without cycles and with the minimum possible total edge weight. Find all the critical and pseudo-critical edges in a minimum spanning tree of the given graph. An MST edge whose deletion from the graph would cause the MST weight to increase, whose deletion from the graph would cause it. Now, this is one problem I had when I first read this, so this is like a hint here. If you delete it from the graph, it will cause the MST weight to increase. It's called a critical edge. A pseudo-critical edge, on the other hand, is that which can appear in some MSTs, but not all. Note you can return the indices of the edges in any order. Anyway, we're not going to bother computing the edges. So here we have an example here. So we have, these are our edges. They're sorted, I believe. Yeah, so sorted based on the edge weight. So here's the edge weight. Boom, boom, boom. Here's the picture. In this picture, you have node 0. So your nodes always go from 0 to n, -1. So like 5, so you go from 0 to 4. One other thing is that this first 0 in these kets, bracket notation, that's what I'm calling it because it's from quantum physics. So the 0 is the index that this edge appears in. So like this is the 0th index. This has the edge weight 1. It goes from 0 to 1. The first index, so you go to the number 1 where everything's 0 index. So it's the first index is the second element, and it goes from 1 to 2 and has edge weight 1. So this is the edge weight, the second number, and the first number is the what's it called? The index in the edges list. So okay, so this is representation, right? So you can get a couple of minimum spanning trees from here. You can do this, you can do this, you can do this. So the critical edges are these two, 0 to 1 and 1 to 2. They're in every single minimum spanning tree. 2 to 3, it's not in all of them, so it's pseudo-critical. 0 to 4 is not in all of them, so it's pseudo-critical, and 0 to 3 is also pseudo-critical because it's not in all of them. So you have at least 2, 3, 4, and 5 are pseudo-critical. Yeah, so 4 edges are pseudo-critical, and these are referring to the index of where the edge is at. Okay, so alright, so okay, so notice that the two edges 0 and 1 appear in all MSTs. Therefore, they are critical, so we return the first line of output, 2, 3, 4. And then if they all have equal weight, this one's just another example. These all have equal weight, so they're all pseudo-critical, all 4. But let's just do this first example. So the first trick to really be able to do this is to not really worry about computing the edges in the minimum spanning tree. The most important thing is to calculate the minimum spanning tree value. So let's just look at that real quick. The code to do that is very simple. To calculate the minimum spanning tree, it's just using Kruskal's algorithm here. And when you use Kruskal's algorithm, you use union find or a disjoint set. And if you use a disjoint set, here where I'm just initializing a disjoint set. So I have a class for disjoint set, and here I have my function that initializes the object. Basically, the idea of the disjoint set is to use union find to be able to do it. and then you're going to use it down here. But we'll get to that in a minute. So when it initializes it, all I initialize is basically this array of parents, which is all equal to -1, which means they are all right now root nodes in their own set. And then also ranks, I set them equal to 1, but this is going to keep track of the size of the things. I sometimes think rank refers to height, but I'm just going to let rank refer to size here. And then, because that's my ranking system, I think it's a little bit of a vague word, depending how you're going to rank your sets. Anyway, so I go down here, so edges, I call this edges, I don't know how to say that, but yeah, so I've sorted these edges because it's the first part of Kruskal's algorithm, is sort the edges. These edges are already sorted, so the edges would look like this, but except actually when it sorts it, it's going to be in descending order, and the reason for that is because, it's going to be in ascending order, so it'll be in this order. So then we basically take the total value for the minimum spanning tree, and we take our two vertices, u and v, and the edge weight in the edges, and then once you do that, you start using your union find class. You want to find the parent for u and v for both vertices. So when you call find, you got this. So this goes into a whole thing, but basically what this is doing is okay, so yeah, so you want to find a parent. So so first I'm going to say what this returns. So this should return, if you have, there's articles I can use for this. Let's see, union find. Maybe this one will work. Because I just need a picture, and well, I just have a picture to help understand. Alright, here we go. So yeah, so this is basically it. So if you have these three elements, then you do a union. But before you do a union, you do a find. So you find the parents for these. Right, so you're like, oh, the parent for 0 is 0, the parent for 1 is 1. So how do you do that? Well, you call find, you get a start node, and then you look through the parents until it's -1, because whenever you get -1, that means that it's a root for this disjoint set. Obviously, at the beginning, the parents are going to be equal to -1 instantly. So, you know, we don't want to do this. This part is going to have to do with path compression, which basically what this will do is, I'll get into path compression, right, and then you return v. Okay, so what does this path compression do here? I should probably say this. This is path compression. So yeah, so you define the parents. Now the parent for u and v, if we're talking about the first one, 0 and 1, it's going to be 0 and 1. They are not equal. This equal thing is just checking if they form a cycle. So to form a cycle, you'd have something like here, 3, 2, 1, 0, right? Or what's another way to do this? Here. If it formed a cycle, oops, should have thought about this, that you can't just like say this, you have to show this. I want to do that. Oops. Did I mess this up? Did I mess it? Okay. Go to here. Okay, so if I were to show a cycle, I would say I have 1, 2, 3, right? And I say these are connected, so this is the parent, and this one goes here. So 3 goes to 2. So basically, if 1 and 3 have the same parent, like the parent of 3 is 1, and the parent of 1 is itself 1, so they have the same parent. If you're unioning 1 and 3, they're already in their own disjoint set, so that's going to create a cycle. So that's the cycle detection right here. So this is what this is doing. It's checking for a cycle. If there's a cycle, just continue. There's no reason to union. Anytime you're unioning, you're really adding that edge into your minimal spanning tree. Also, one other thing I forgot to mention is that Kruskal's algorithm is basically greedy, so it's just, that's why we sort these edges, so we always want to start with the lowest weights first. So we want to add the lowest weight first, so like you add this one, then you'd add this one or this one because they have equal weight. So yeah, so, and then, you know, total weight plus or equal to right. So when you union these, like here, what I have is I have this thing called path compression on my find. What my path compression does is, here's an example, this talks about it right here. So I'm calling find, and it's calling for, let's say, element 3. And right now you have, all of these are connected to the 9. This is the parent. When you call find for 3, you go up, you find the parent is 9. And what you do is, so I look here, so my start node would be 3. I go through my parents, and I say, wait, my start node is not equal to the node that I end up with. So what I'm going to do is say, hey, set the parent for my start node index equal to the V I'm at right now, which is 9. So that means the 3 is going to point to 9 now. And that's compressing your path. That way, anytime you're traversing through here, like let's say you call 1, you call find on 1, it doesn't have to traverse all the way up here. It just has to traverse through here. And if you call 3 again, well, you know, it's very easy. So, so that saves time for your find, and that's the path compression. That's part of the optimization of union find. The other thing is you're going to call union, right? So when you call union, you're going to do it based off of the rank. So this code really is just going to, basically what this code is supposed to do is if it has a larger size, I'm going to attach it to the other one. So like here, basically. So since this 1 is 0 is larger, I'm going to attach the 2. If I union 1 and 2, I'm going to attach the 2 to the 1. Instead of the 1 to the 2 or whatever. Because if you attach the 1 to the 2, you get this craziness, which is obviously going to be hard to like do find on 0. It has to recurse all the way up. And that's where the improvement comes from. You can this union find with path compression and union by rank basically has a time complexity of like log v, where v is the number of vertices, versus what you originally would have, which is like O of linear through linear scan of the vertices. So that's a good improvement. But yeah, that's what Kruskal's algorithm is. So Kruskal's algorithm is basically calculating the minimum spanning tree value and so on. So first thing I do here, so now how am I going to find critical and pseudo-critical? So at first I'll find MST by calling Kruskal. So I'm going to start with some critical and pseudo edges. And then I'm going to go through the length of the edges and basically increment them by 1. Mainly the idea is just, I'm just incrementing by like epsilon, and I'm just increasing by some small number. I choose 1, doesn't matter. The main point is that once I increment by 1, if I compute ST again, if that ST value changes, then that means that the original minimum spanning tree, like this is not a critical value, right? Because that means you didn't need this edge. Like if you increment this one by, and this one goes to 2, that should change the value of the minimum spanning tree, because that was in every minimum spanning tree. So now it should be 8, right? So if it becomes larger when you do this, that means that that's a critical edge, right? And I just decremented by 1 to like keep it down. And then here, this elif is checks that ST is equal to MST. Now this is for checking if something's pseudocritical or not used at all. So like consider the 6 here. If you increment this by 1 and it goes to 7, well, it was never using that edge in the first place in the minimal spanning tree calculation, so that doesn't affect your results. So ST should be equal to MST. And then for these other ones that are pseudocritical, like this one, you don't need to use this edge. So if you increase this by 1 and it goes to the edge weight 3, it's just going to use this edge, right? It's just going to use a different path. It's not going to do the 2 to 3 path. It's going to do this path, right? And this is not you ignore the 2 to 3, or this path. It ignores the 2 to 3 edge. And by doing that, you should realize that's pseudocritical. But at the same time, it doesn't help you because you also don't realize if this one's not used at all. It's not pseudocritical. So to determine that, you can subtract it. So take your current edge and then subtract it by 2. So if you add by 1, so basically what I'm doing is I'm going less than its original value by 1. And the goal here is to see if you make it smaller, is it going to actually reduce the minimum spanning tree? Like, are you going to get a minimal, an even smaller minimum spanning tree? Because if that's true, like if you decrement this one to a 1, like obviously now instead of 7, you're going to get a minimum spanning tree with value 6. So if that happens, it's pseudocritical. But if it's something like this one here with the 6, if you decrement that one by 1 and it goes to 5, it's still not going to use it. Yeah. So, and since everything is an integer, that's why I can really use this decrement by 1. Like, it could be argued that why don't I decrement by a smaller number, but it doesn't really matter because these edges are not decimal numbers. These edges are integer values. The edge weights are. So you should be fine, because if you have another edge that has 5 and you decrement this one by 1 and it goes to 5, you know, it's not going to change it. But that's the thing here. So like, if you decrement the edge by 1, if the minimum spanning tree doesn't change, that means you're never using that edge. If it changes the minimum spanning tree, that means it's a pseudo-critical edge. So that's why you want to append to pseudo. So yeah, so this code actually works. But the good thing about doing this problem is really it has pretty poor time complexity, because you're searching through all these edges, and then you're running this, which is like this sort here is going to be like E log E, and these union finds are like log E. So this is like E log E here, E log E here. So this is like E times E log E. So I think it's like E squared. So I think this is E squared log E time complexity. Taking up a little bit of space here. You can kind of see the memory I'm taking up, the runtime. But yeah, this passes the test. This is a very good problem, though, to learn how to find minimal spanning trees and how to optimize the union find method. But yeah, that's cool.